Last section of chapter 1. This is section 1.7, solving geometric problems involving roots of complex numbers. So before we actually go through example 18, we'll just look at some key facts that you need to remember. So if you are solving z to the power of n is equal to a complex number, so for seeking nth roots of this complex number, you have n of those roots, and these roots will form a regular polygon centered at the origin with n vertices. It's very similar to what we mentioned before with the roots of unity. If you've got n roots of unity, you're looking for the nth root. Here you've got the 6 of them. They are also centered at the origin, and you have a regular hexagon or regular polygon with n vertices. Notice with the roots of unity, you will always start from 1 and then go every equal amount of around the origin to the next root. With the nth root of another complex number, this is the same regular polygon but slightly shifted. So you start from the first root, and then the next root is the same amount of turn as you would have had in the roots of unity. So here, if you've got hexagon, you're going to have every 60 degrees you'll find the next root. Now there is a very, very close connection between the two. As you can see visually, you get the same shapes. This one's slightly rotated. Now if z1 is one of the roots, so let's say over here we've drawn the first one, then the other roots, you don't need to go through all the solving as we talked before. You're going to find the second root by multiplying this first root by the roots that go with the unity. So you just find the roots of unity, the first root of unity, and you can multiply this complex number z1 by omega, and you'll find the next one, and then by omega squared you find the one after, etc., etc. Okay, now if your z1, your first root that you find, is not necessarily the first one that I've drawn here, so for example this one, it will still work. You can still multiply it by the first root of unity, and then multiply it by it again, by omega, then again, till you get to the last one. Okay, so we are going to have a look at, okay, let's move on to example 18. You've got P with the coordinate root 3 and 1 is a vertex of a regular triangle, equilateral triangle centered at the origin. So there's 3 of those roots, so it must have been a cube root. Find the other 2 vertices and then find the area of that triangle. So this could be your z1, so your first root of cube root of a complex number. We don't know which one, but we haven't been asked to find it. If you were, we would just need to cube it and then find the what number was cube rooted to give you this one. Okay, so let's find the argument and the modulus. So modulus is going to be root 3 squared, add 1 squared, square rooted, so that gives me 2. And the argument over here, let's just do that quickly, that's going to be root 3 over here, 1 over here, so it's going to be arc tan of 1 over root 3, which gives me pi over 6. So this is my complex number, one of the roots. To find the other roots, all I need to do is find the first root of unity that is not equal to 1 and multiply, let it be equal to your omega, and then multiply z1 by that. So we need omega, okay? And the omega is simply e to the power of, remember the formula, 2 pi over n, so it's 2 pi over 3i. So this is the first one that's not on the real axis. So all I need to do is now do z1 times omega, and that will be my second complex number that will go to the second vertex. So this is going to be 2e to the power of pi over 6i multiplied by e to the power of 2 pi over 3i. So this is 2e to the power, add these two numbers, that gives me 5 pi over 6i. So it's going to be somewhere here, because that was pi over 6, this is 5 pi over 6. So because that was all the way here, just do it in a different color. That's 5 pi over 6. So that's my second vertex. We are going to find the coordinates of that point, so you just need to transform it into, use the trigonometric form and substitute the argument and the modulus into that. So this is going to be 2, this is going to be minus root 3 over 2 plus I, sign is still positive a half, okay? But you could have actually worked this out by doing a symmetry here. Let's just see whether it's going to be minus root 3. It is, add 1i. There you go. So this is my second vertex. This is the coordinates. Let's write it in coordinates, because we've been asked to find the vertices. So minus root 3, 1. And then finally we need to find the third one. So that's going to be, let me do it in a different color, z3. Okay, so this time you can either multiply z1 by omega squared, or you could do z2 by omega, whichever way you do it. I'll do z1. So it's z1 was our first complex number, so 2e to the power of pi over 6i. Let's multiply it by our first root of unity to the power of 2. So you're going to have pi over 6i multiplied by e to the power of 4 pi over 3i. So adding these two together, you're going to get 8 plus 1. So it's going to take you to 2e to the power of 9 pi over 6i, which is 3 pi over 2i. If you adjust it by taking pi minus 2 pi from that, you have 2e to the power minus pi over 2i. Substitute it into the trigonometric form, which you could have done by using the other argument. It doesn't matter. Any argument that takes you to that position is fine. So cos is equal to 0, and it's 2 times sine is going to be minus 1, so it's minus 2i. So the coordinates of the second complex number, the third vertex are 0, minus 2. So there you go. So this is going to be minus 2. psi, the coordinates 0, -2. Now finally you've been asked to find the area of this triangle. So let me just move it across here. Hopefully you can still see it. Okay, so the area of this triangle, base times height divided by 2. So base goes from -√3 to √3. So that's going to be 2 lots of √3 multiplied by height. So it goes 1 and then 2 more. So it's 3 over 2. So it's 3√3. So this takes us to 1G. Splendid.